Hey everyone, thank you for joining again for the Raspberry Pi Pico live stream where we are trying to create this emulator. Before we get started, just let me know if you can, so please write in the chat if you can see me and hear me correctly. I'm seeing there are already some people here writing in the chat, and today we have red lighting for the show apparently. So as soon as I get your confirmation, hey Costa, nice. Hey Nikari. So as soon as you let me know that you can see me, we can get started. Meanwhile, let me share my screen. So now you should be seeing my screen, hopefully. Yeah, you can hear and see me fine. Thank you. This is the second time I'm doing this stream. Last time was pretty intense, and I'm happy to I was really excited about all the feedback that I got. Apparently one of the guys created their own Raspberry Pi RP2040 disassembler after watching the live stream last week. They did it in Python. They shared the code with me. It's I put the link on the Hackaday page, so that was really cool to see. And I also got some questions. So before we dive into the code, let me just real quick cover these questions. Just as last time, I will be monitoring the chat as we go. So feel free to share your ideas and opinions on whatever we are doing. So last time we built this project. Where was that? We started building this simulation project, and we used TypeScript for writing this code. And I figured out by the questions that some of the people who watched the stream were not really familiar with TypeScript. So a word about TypeScript. TypeScript is basically a language that compiles to JavaScript. It's essentially a JavaScript with type checking. So once we run the TypeScript compiler, it returns JavaScript, and the JavaScript that it returns looks very similar to this code. The only difference is the type annotations. Like here, they are removed, and there are like a few other syntactic sugars that TypeScript adds, and these are removed or changed. Like the code is rewritten when it translates to JavaScript. But for the most part, you can assume that we are just running JavaScript here. And by the way, I can just run the TypeScript compiler, and we will be. Oh, I need to. So let's do this. I haven't set up a TypeScript project last time. I just, installed some packages and built it all as we went. But the easiest way to set up a TypeScript project, I think it's tsc init to create an empty configuration file. Let's see. No. Yep, there is probably a way to initialize it. But minus init, yep. So this creates an empty configuration file with a bunch of options. I think for the most part, we can say we are targeting modern JavaScript. And then one thing, okay, let's not care about the rest for now. And then if I run the compiler, maybe we will just specify the out there, so it will write the compiled the JavaScript files inside the this directory. And as soon as I run this compiler, you will be able to see like what a compiled file looks like, and they look pretty much the same as the TypeScript code. But as you can see here, there are like no longer have these type annotations. So this compiles to this, and I think it removed, oh, it even preserved the comments. Let's just add this directory to the gitignore, so it won't be committed. And one of the people who watched the stream last week, they asked me, too bad we didn't, I wish we created a project in Rust so it could compile to WebAssembly. So if you don't know WebAssembly, it's basically some kind of virtual machine that runs in web browsers. So an alternative to programming web pages in JavaScript. And the good news is that if we really want, there is a project called Assembly Script that can actually compile TypeScript to, or a subset of the TypeScript syntax. It can compile it to WebAssembly. So we are not going to do it right now, but just so you know that even though we write in a high-level language such as TypeScript, down the road, if you want, we can compile this to WebAssembly. But right now, we just want to get it working. So let's just have a quick look at what we did last time. And then I will show you what I did since then, which is not too much. So basically, we created this npm start. We created this simple program that loads blink and blinks. It like simulates the main method of blink. And we got it to sort of work. We did a few shortcuts, but we got it to work. And in order to get that to work, we had to implement the CPU registers, the flash, the SRAM, and also start simulating a few instructions. I think we implemented 6 instructions. And this one is just like stub implementation. It doesn't do too much. And we also started writing tests to our instructions to make sure that they work correctly. So we could iterate faster and not worry too much about whether the implementation is correct or not. So that's what we did last time. And as we finished the session, I created my initial commit, and then I pushed it to GitHub. You can find a link in the video description from last time, if I'm not mistaken, or you can find it here. So the only thing that I did since last week, I just went to this package.json file and I added a few fields like the description, the repository, the keywords. So nothing really too interesting or too major. And I think I added this link to the README file. So the project is pretty much at the same state as we left it last time. And for today, we are going to try and get the UART peripheral. And UART is basically the serial output, and that would allow us to get debug prints from the program that we are running inside the simulation. So in order to do that, first of all, you can see that we have I have updated my Chrome, so now the table of contents on the left side, not the right side. They refreshed the user interface of their PDF viewer. And I have here the list of peripherals, and the second one is UART. So they are like, we can see that there are 2 instances of UART. So we have 2 UART peripherals. And okay, they have all of these features, and and there is like a GPIO muxing table. So unlike Arduino and I think most other chips I worked with, there is actually, we can decide which pin will have the UART function. So for instance, for each of these GPIOs, we can decide like what it will do. So for GPIO 0, we can decide that it will be either SPI 0 RX, UART UART0TX, and etc. And speaking of just UART, we can see that like UART0TX repeats 1, 2, 3, and I think 4 times. So there are 4 different pins that can function as UART0TX, and same goes for the RX and the other pins. So there is no specific pin that is assigned to UART. Rather, we can decide to connect it to one of few pins. So we'll probably need some register to control that. And what else? So UART, blah, 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 blah. Okay. Let's have a look at the registers. UART operation. Okay. Error bits. Oh, interesting. Okay. So, where is the registers? Let's get to the interesting part first of all. So yeah, there is like a bunch of registers. I think the interesting one is the data register. It basically holds the data that we received or the data that we want to transmit. So we'll probably have to look at that in order to get the data transmitted from UART. And then it says that the UART0 and UART1 registers start at these addresses. So we'll have to intercept memory reads and writes from this address and this one in order to listen to these registers and implement UART. And I think just like last time, having a specific goal in mind that we want to achieve will help us stay on path and will basically help us focus on getting to our goal. So for today, I decided to try and get where is the examples? So last time we did blink, and today I want to try the UART, hello UART example. Let's open the source code for that first. Yeah, it's tempting to start with the assembly version, but let's do the source code first. So basically, it's a pretty simple program. We can see it's using UART0. It's using pin 0 and 1 for the RX and TX. And this is the baud rate, and we can see that it initializes the UART. It's set the functions of these pins to UART, and then it calls a few library functions to print a bunch of characters. And just like last time, we are going to take a look at the disassembly of this code. So let's put them side by side. And why doesn't it close? Okay, yep. Let's put them side by side, and just like we did last time, cheat and go directly to main. And perhaps next time we'll already go to implementing all the stuff that happens before main. But for now, let's just stay focused on main. And we can already see some very familiar instructions. In fact, I think we have MOVS, we have push, we have LSLS, and I think this is the first instruction that we actually need to implement. But before jumping into implementing the instructions, let's just have a look, overall look at what kind of instructions we will need to implement. My estimate is that it would be like a few more instructions, maybe 10 in order to get that to work, but maybe I'm just too optimistic. So the first thing we can see is that it's calling the UART init using BL. So UART init wasn't really inlined. Last time the compiler inlined a few functions, but this time it didn't. And then another thing we can see is that another thing we can see is that we have a few more instructions like CMP that we need to implement, all those conditional branches, and what is UXTB? We'll have to look it up. A few instructions that I don't even recognize. Interesting. Yeah, but we have a bunch of conditional branches. These are probably coming from those UART puts and UART puts, putsy and puts. There is probably a loop here, so that's why we have all those conditional jumps. And actually, you know what? For starters, I think we can still skip like those branch instructions because we don't really need those at the moment, I guess. We are only interested in getting the output from these function calls. So maybe we will leave the branches for later. And the reason for that is that if we go to these branches, they are probably using some other instructions that we still don't have. So let's leave them alone for now and focus on all those exotic instructions. Oh, and one more thing before we dive into the implementation, I can see this constant, and if you remember from the datasheet, it's the base address of the UART0 register. So this is a good sign. It means that this code is actually going to write something to the to that register. Actually, I think we might encounter an interesting problem here with the string. If it's somehow coming from the RAM, because if I'm not mistaken, this is a RAM address, so it's doing something with the RAM. Let's see, where is that address referenced? This is this address. Okay, that's okay. So this is like after this GPIO set function. So it's probably loading something. Oh, it's loading into R3, and then it's loading data. So there is a good chance that we are going to get some garbage because nothing will be loaded to the memory at this address right now. But let's start and just implement this logic, and then we'll try to figure out perhaps we do need to run some of the initialization code before main in order to set up the RAM and get these prints to work. Okay, so no messages in the chat, and we can move on. So the first thing we'll do before we jump to implementing them is just to copy the hex file. So that's hello UART, hello UART.hex, paste it in, and then okay, let's just close Telegram so it won't bug us. Okay, so we have this one, and then instead of running Blink, let's run hello UART, and we need to set the address to the address of main. And where was main? Main was, oh, it's the same address. Easy, cool. Nice that to have main at the same address. And then if we execute it, let's just run the first few instructions. We can see that it prints a few BLA ignored. That's because we have those branches here. But I think one useful thing to do would be to print instructions that we don't recognize, so we can quickly spot those, the instructions we still haven't implemented. So in order to do that, let's add else console log warning instruction at this PC is not implemented yet. Okay, cool. And then we can see that we have a bunch of them. Like, I wonder, interesting. We are not simulating the address space of the flash, and that will probably bite us soon, but let's first implement some more instructions and then worry about that. So this instruction is not implemented yet. That doesn't make sense. Oh yeah, I need to print it as hexadecimal, the string 16. All right. And let's see. Okay, this one probably makes more sense. Okay, yeah, so that's the LDR, and we already spotted that. And then 37A, that's 37A. Oh, that's a part of the BL. There is a bug here. We should skip this instruction if we see that there is a BL. So yeah. So if we ignore a BL, we should also increment PC, so it doesn't try to execute the next opcode. And then we can see that if we are running for, where is it? Yep. If we are running just the first 10 instruction, then there is only this LDR missing. So let's implement LDR. And we'll do it the TDD way. So LDR, let's put it here. It should execute, and where is LDR? This is LDR, so this one probably. Okay, so loading this value from the current location plus this constant into the current like PC plus this into R0. So as usual, copy paste, and then we can say this is the opcode of this. So LDR, and then okay, so loading this cool, expected 80. Okay, we still haven't. And then we also want to put some data into this address, so rp.flash at flash at this index equals 42 hexa, and then eventually we probably expect R0 to equal this value, and we need to define the constant for that. So R0 is just register number 0. Okay, and I think that's the test case. We can also assert that PC was incremented by just 2. Okay, and now we need to implement this instruction. Let's focus on this test and open the file. LDR. Okay, and let's check out the datasheet to see how it's encoded. Instructions, I think it was A5. There was a list of all the instructions, maybe A4. Oh, maybe A6. Oh, finally. So LDR, there are a few variants. So I think this is the right one. Loading from register into register, from register plus immediate value. Okay. So that would be the opcode. if opcode equals to this, then so that's probably not the right one, because we see that this line is not executed. So maybe one of the other variants, even though it looks pretty correct to me. Did I miss anything? Let's check the other options. So this one doesn't look right. And no, this one doesn't look. And that wasn't an LDRB, right? It was an LDR. Let's just print the bits of this. This opcode, so 01001. So yeah, it's not this one. 01011 01001. So this is the okay. Oh, right. Load register literal calculates an address from the PC value and immediate offset. Loads a word from memory and writes it to the register. So it makes sense. This is, let me make the font larger so it will be easy to see. So this is the right variant of LDR. This is the one that we are using here. Yeah. So yeah, we can see now we have a match. And then what do we need to do? LDR. So align PC4. Address if add, then else. What is add? Add is always true. Okay, so that's always true. Zero extent. So first of all, we already had this thing. The addresses need to be aligned to the word offset. So that's like 4 byte, 2 byte. Yes, 4 byte offsets. So that's why they are adding like 0 bits to the right of the value that we get here. Okay, so we have IMM8, which is just like the lowest 8 bits. So that's opcode FF, and then that would be shifted by 2. And then we have this RT, which is a constant. RT is these 3 bits, so opcode shift right 8 %7, and then we need to do RT memu address. Okay, so I think we already have like we have a function to write uint. We need a function to read uint. We'll add that in a moment. So we just need to this.registers RT equals this.read uint32 at this.pc plus IMM8, I guess. Read uint does not exist. Yeah, we need to implement that. Okay, so read uint address number value number. Now I said that it will bite us, that the fact that we are not using the correct address for the flash, and I think this is the first time we have to deal with that. So basically for now I will just I will still go on with this, and I will say this: if address is less than this address, we'll just assume it's a flash address, which is incorrect. That is that the correct number of zeros? Yep. We should just in this case we should actually read from the boot ROM, but for now we'll just like read from the flash. We need to read so yeah, we need to read words. So let's create another view of the flash data view, new data view that will allow us to this flash to do word uint 32 reads. So flash view, okay, and then inside here dot read get uint 32 at a given address. We don't need a value because we return it, and we want that to be little Indian because we have been beaten by this already. And then now we will start accounting for the real flash address. So eventually this will be should be reading from boot ROM once we have it. And then this one should maybe, okay, address. This one should just read from the flash, but now it should read like we should subtract this value from the address to get the flash offset. And we don't need it right now, but we'll probably need in a few minutes. So let's already go with the SRAM. So we have constants for that, so maybe we should use them instead of like those magic numbers here. So if it's greater or equal, then and it's oh, nice. We have the condition here already, so just read it from the SRAM view and address minus RAM start. Okay, cool. It's not happy because we need to read it from the SRAM view, not from the SRAM. Cool. Okay, and then we still have implement IO space reads or SAO space reads once we need them. We don't need them at the moment. And let's declare a constant for the flash start address. Export. Nice to see this starting to get more organized code base. Okay, so flash start address, and now we have a problem because right. So let's just, if the address is invalid, we still need to return some value. And I have no idea what ARM does when you're reading from an invalid address. I guess it depends on the exact address space. But for now, let's just return all Fs. If anybody likes to just, Google that and let me know what the correct behavior would be, that would be, or, just maybe it's somewhere in the datasheet. I have no idea. Let's also add a warning, read from invalid memory address and print the address. Cool. Okay, so now it should. Okay, so one thing that oh yeah, there is another issue here. Need to give it the buffer. Okay, finally the test is running, and let's just focus on this test, and we can see it's failing. It's expected 66 but found this value, which is probably FF. And let's look at the console output. Why did we print this value? Oh, that's in the test case. Never mind. Yeah, it got an interesting value in R0. Why is that? Let's take a look at the values of these. Let's see. IMM8 is 148, just as the instruction dictates, and RD is 0, so this is good. And then this.pc should be 0, right? And then we are reading from so it gets to this if case, and this so this is the address. Oh, right, I know. The reason is when we initialize this RP2040 class, we fill the flash with Fs. So we only wrote 1 byte, so that's 42 hexa, but we basically have 3 other bytes that are just F, so that's why let's just try them to just fill from 148 with 0 from 149 to 1. Okay, we can fill the rest of the flash with zeros as well. That would also do the trick, but let's just make it the minimal amount of setup that we need to have this test passed, and voila, we have LDR implemented and working, at least so it seems from this test case. Let's just verify it by running the program. npm start. And now one thing I want to do here, I want to print the value of the register, and we'll see if we know it's 0 in this program, and we'll see if it's, let's print it as hexa. We'll see if it makes sense with the actual program. So this is the value for 1046 is 0, and if we go to the disassembly, yeah, there is this value. Interesting. It's close enough, but it's not the same value. Let's see. Where are we loading from? Maybe we are reading from the. So this is this first LDR instruction. It reads from this address. And what's in this address? Yep, we have this value. So why do we see this value? It's not too far away, but it's not the value we anticipated for, right? Interesting. What could that be? Let's start by printing the content of this address. That's the run blink. So as soon as we start a code, console log mcu.flash.flashView.getUint at this address, and it's Little Indian. Yeah, and print it as hexadecimal. Yeah, that's the correct one. So that's what we expect to find here, and we are reading it into R0, right? The R0. So it makes sense to have this value in register 0. Okay, so more debugging. Let's print this value and see if we are reading from the right location. 40A, and that's 40C. Yeah, so I think what happens here, let's check if, yeah, I guess it, oh, align PC4 maybe? Is this aligned to 4 bytes? No, so we need to align the value that we get to 4 bytes. That's the thing. So we can say something like, so basically, and then I have no idea if that's the right thing. Okay, so yeah, let's first add a test case for that, and then we can implement that. So basically, the test case would be the same, but this time when PC is not word aligned. This time PC is not going to be word aligned, or maybe instead of word, 4 byte aligned. Okay, so oh yeah, good catch, Afir. He said on the chat, what's the previous instruction before the data? And that's what we saw. So okay, so we need to load that, and then just, you know, start from PC equals 2, and then 150, 51 to 53. No, we need to, this needs to be aligned, or maybe I think this doesn't divide by 4. Oh, it does. So yeah, so this is the correct test case, I guess. So in this case, it would read from 152. It's going to, how does it align? Is it aligning up or down? Where is this? I think there is like maybe here, like explanation of this pseudocode elements. To a multiple, okay. If x is real, round up, round down, align by Okay, so does it round down or does it round up? This sounds like it rounds. It rounds down. Oh, that doesn't make a lot of sense. So, maybe that's not a problem. If it's rounding it down, then if it rounds it down, then it should have read from this address. So maybe there is another thing. Maybe we are the offset here that is relative to PC is actually added to the PC of the next instruction. Let's take a look at another example to check that. So here we have this address plus. So do we have node here in this? Yep. So we have this address plus this value, and this resolves to, so the difference here is 2, and here we have this address plus this value. Okay, too much copy paste. Let's try that again. 380 plus that was and it resolves to 4C. Yeah, so based on these two observations, I guess we should just add 2 to we should just add 2 to PC, and we will also align it because the datasheet says so. So let's remove this extra text and fix this one. It should read from this offset. So 150 from 51 to 54, and then here we need to okay, we need to add 2, and now the test pass, but something else fails. Oh, okay, this. Oh, why did I delete then? Okay, nothing too important. I didn't delete anything too important. Okay, so we need to delete the second test case that we just added because we don't care about it right now. Okay, and now let's just make sure it reads from. Actually, we can add another case for that case for non-aligned read. So rounding PC down to be 4 byte aligned. So if the instruction was in offset 2, we would still expect. So wait a second. Is the PC aligned or the address aligned? I'm not sure if it. No, it shouldn't make any difference because this one is always like divisible by 4. So yeah, so it makes sense to. That was the second one. It makes sense that yeah, PC would be aligned. So so if PC is 2, then we still expect it to do the same basically. And then we just need to align this to 4. So minus this dot PC 4. Okay, and it still doesn't pass because now we started from 2, so it goes up to 4. Okay, cool. So hopefully now we don't need this to be let. Can be a constant. So at this point, hopefully we have the correct implementation of LDR. Let's see. This is the value it has loaded, and it should have loaded. Oh, it's still the same as before. Why is that? It loaded from 0 OA. Interesting, all this work. Maybe I didn't save the file before running again. No, all this work and we still got the same issue. Maybe it has to do with this. Yep, right. Oh yeah, I'm not printing the right address anyway. Print error. But yeah, now it read the correct value. So there is some issue with my code that aligns the PC. Maybe word aligned means aligned to, no, it said aligned to 4 byte. Yep. So how? What gives? Okay. So we have this instruction LDR, and it's here in this address, and this address is obviously, oh, right, we are reading from this address. So we first need to we first need to add it too, because that's like, let's call it next PC this.pc plus star, and then apply the alignment PC plus next PC. Okay, now I think it will make sense. Minus. Okay, now I think it will make sense, and now this is actually yeah, so now PC is actually 2, and it should align it. So let's see, how does the test change now? Because now the test is incorrect, so that would be reading from 2, and 2 will be aligned to 0, and then 0 plus this value. So we'll read from here, and we'll read from here until here, right? That should be 0. No, need to zero out the next bytes, and now it passes, right? So yeah, so now hopefully we implement this instruction correctly, and this test case also tests like this alignment. So we can again discard the second test case. We might want to add another test case where it's actually aligned, but it's not really important now. Let's see if the code, yeah, it runs, it reads from the right value from the right address. And yeah, that was a long time to implement one instruction. But we learned a few things along the way, and now we are ready to move on to the next one. And the next one, let's read 20 instructions this time and see what we are still missing. So 390, what's that? What's the next instruction? 390. Okay, that's another LDR, but this time the other variant where we are reading relative to a register that is not PC. So let's create a test case for that. And this one is this. So this is the test case, and then this is like the instruction. Okay, and then we can say something like that. So that's the instruction, PC is 0, and we want to set up R3 and R2. So in this case, let's do it more interesting. Let's set R3 to point into the RAM. So registers points to the start of the RAM space, and then oh, that's R2 because we are reading into R3, and then we can say .sram at 24. So that's this R2 plus 24 will be 55. And then after running this instruction, we expect R3 to contain this 55 value. If I understood correctly how this works, let's just define 2 more constants for R2 and R3. Actually, let's also define R1 because I know we'll need it sooner or later. And R7, so we'll have all these registers handy at hand. Okay, and now we just need to implement the second instruction. So that was LDR literal, and this is LDR, no, yeah, that was one of the, what's the difference? Yep. That was yeah, that was LDR literal, the one that we implemented now, and we need to implement also LDR immediate. Okay, and hopefully that won't take as long because we have already done the hard work. So that's the encoding. Let's focus on this test for now. No, it doesn't match. Why doesn't it match? Yep, we forgot to copy the opcode. So this is the opcode, so we are not running the correct opcode in the test. Okay, and now we can see that it actually runs the code inside this if. And we need to get RT, RN, and IMM5, and I think we have already done this before, so we can just copy paste and hope we are not doing it incorrectly. Let's just verify RD, then RM, and then IMM5. So here it's RT, RN, RT, RN, and IMM5. Yep. And then basically, okay, if add and probably as add is true, so it's always true, then RN plus IMM32. And IMM is always 0 extended, so we need to 0 extend it, like shift it left by 2. Okay, and address if index, then offset. What is index? Index is true, so address is offset, and offset is RN, and then piece of memory into RT. What is wback? Wback is false, so we don't care about that. Okay, cool. So basically we just need to do something like this. Registers RT, address, and address is just that's RN plus IMM5, right? Or maybe not so, because the test doesn't pass. So let's see. Oh yeah, we need to read the value of these registers. Okay, test passes. That's cool. Let's have a look at the chat. Oh yeah, that's the guy with the Python version of the project. So yeah, Jason, that's cool. Feel free to share the link in the chat so people can actually see what you're doing. Okay, so running this again, and interesting. We have read from this memory address, and this memory address happens to be just this value plus 24, right? So this plus 24 to string 16 is exactly this address. So it seems legit. It seems like we are doing correctly so far. And then we have a few more missing instruction. 392. That's probably the branches. Let's see, 392. TST, yeah. So I guess TST compares the numbers. Let's take a look at the datasheet. No, let's first create a test case and then take a look at the datasheet. TST. Let's put it. Yep. Let's put it at the end. I will try to keep this sorted. Let's move this one to the top, so the instructions will at least have some order, not just random order, but sorted more or less. Okay, and then this one would be the TST, so that's the TST R1, R3, and that's the opcode. So this is the opcode. And we need to set up R1 and R3, and let's just make them different for now. And let's see. So I think at this point we will have to worry about the flags that we neglected so far, because I think that's the purpose of TST. Fortunately, we don't have to. Let's just read about this APSR register before we jump to implementing it. And we also need to figure out what to assert on this test case. Okay, cool, Jason. ASPR, where are you, ASPR? ASPR, whew, that's long. Yeah, ASPR is the Application Program Status Register, and it's a register with 32 bits, but most of them are useless. We only use the 4 high bits. We call them N if it's a negative, Z if it's 0, carry if there was a carry, and overflow if there was an overflow. Okay, so let's just implement this by adding I guess another register to our CPU. So public ASPR number, and it's reserved. It doesn't say anything about the value of the reserved bits, right? Reserved system features, the spatial, currently, software, read. Okay, I guess we don't need to worry about that too much right now. So let's just initialize that with 0. And then let's take a look at what TST does. TST, where are you, TST? TST register. So this is the encoding, and yep, it just updates these flags. Cool. So maybe we can create some shorthand getters for looking at the flags and setting the flags. I see that this pattern repeats a lot, where this V is unchanged. Let's just do, yep, it repeats 16 times. Okay, so I think we'll do, we'll create a helped, that was the name of the register, APSR. APSR, that will get N. It's actually a Boolean, C Boolean, and C Boolean, and maybe also V. Yeah, and then this dot APSR equals and I think that would work. No, TypeScript isn't happy about this. Anyway, so you can do it like that. So N is I think the, where is that? We found it before, APSR. Let's just look for the first match. Yep. So N is the most significant bit. So that would be, let's just create constants for them. So APSR N is just the most significant bit. Yep. And then we have Z, which is the next bit, and C and V. So C and V, and then we can, where is this method? Yep. So if n APSR n, otherwise 0, and same goes for, actually I will just call it nzc, and if we need one for v, we'll make it later. So ASPR, so if n then n, if z then z, and if c, APSR c, otherwise 0. And we also need to preserve the value of the other bit, so just let's just you know, copy all the other bits are unchanged, so ASPR and everything except for the bits that we do care about, the ones that we do want to change. APSR C, right? No, we need C and C. Okay. Okay, so hopefully this will update those 3 bits whenever we need, and now we can yeah, I can see that LSLS should do this and MOVS should do this, and we'll get back to them in a few minutes. But first of all, let's do TST. So TST. So if opcode is, let's focus on this test. Oh, we need to finish writing the test case first, right? So in this case, their value are different. So what does TST do? So TST, where are you, TST? TST. So let's see. It does end between Rn and shifted, where shifted is Rm shifted by 0, okay, with carry. Okay, so basically I think it's I guess if it shifts it by 0, then I guess carry should always be 0 because we haven't shifted it. So this is always 0, I guess. And then n returns the, so we do bitwise and between those values, and n returns the leftmost bit, and this is just is a 0 bit. Means if result is 0, I guess, if all bits are 0. Let's just verify this. All zeros bit string. Okay, so that should be pretty straightforward. So in this case, we expect the 0 flag not to be set, and we basically expect the flags to be 0, I guess. rp2040.to equal 0, and this will probably pass because it's already 0. So you know what, let's try when the result is negative. Let's make it a bit more interesting test case. Let's make them make the result negative. So in this case, we expect this z bit to be set. So let's export these consts. So we expect to equal this APSR z. Okay. And now the test fails, and we can happily implement the instruction. So TST, if, let's focus on this test and the opcode, where is that? TST. Yep. And the opcode is this. How many bits is that? That's like 8, too many, 11. So shift 5, I guess, right? And then no, 6, because we need 6 bits for these registers. So that should be this thing. and we can see it goes right into this if, because this test, this code is covered by the test, so that's a good sign. And then we have Rn and Rm. Rn, where are you, Rn? Rn is this one, and then Rm, Rn, and then we need to const result is just bitwise n between their values, not the actual register numbers. Rm. Okay, and then we just need to update the flag. So we can say this dot update nz and c. So n is true if result is 0, and z is true if result, if the most significant bit is on, so if it's a negative number. And I think carry is always false. Let's verify this. Where is carry come from? Shift C. And Shift C gets RM, Shift T, Shift N, which are just LSL and 0, and the current value of APSR. I should stop calling it APSR. Not sure where that came from. So Shift C, what does it do? So if it's LSL, then we do LSLC value amount. So basically, oh, okay, that's interesting. If amount is 0, then results equal. So that's what we have here, right? We have a 0. So if in case it's a 0, the result is equal to value, and carry in is equal to carry out. So yeah, this is just a very cryptic way to say that this flag is also unchanged. And for this, let's make a simpler method that let's make another simpler method that only takes n and z, because we don't need to change c here. And let's make that method date nz and z, and we don't need a c, and we don't need a c here, neither here. Okay, cool. And it even fits in one line. Nice. Cool. So in this case, we just update, and TypeScript doesn't like it because it expects a boolean. So we can do that, or we can do that's the JavaScript way to convert a number into boolean, just twice boolean not. And now TypeScript is happy. And the test passes. So let's add one more test case where they are actually equal. When the registers are equal. So in this case, why isn't it happy? Oh, I'm missing a comma, of course. In this case, let's make them 55 and 55, and now since they are equal, actually I think I have a bug in the test. This should be true if they are equal. So in this case, it's n that should be the result should be just the n flag, and in this case it should be z. So I had a bug in the test and a bug in the implementation. How nice. But luckily I wrote another test, and now I need to import this one, and now it still doesn't pass though. Let's see. Expected this, received this. So update n and z, and n So let's focus on this test for a moment and print the value of n. We expect n to be true and z to be false, and this is the case. So why does the test fail? Maybe it has log rp2040 ASPR to string 2. Okay. Why is it negative? Yeah, because that bit is set. So why it is not? Why? Let's just try to write it as a bit mask. I guess all those bitwise operations actually mess up with the sign. Let's just print the intermediate results and see what happens. So yep, this is probably positive, and then when we do this, it probably gets screwed up somehow. Yep, this bitwise or makes it negative. So I think maybe it has to do with the not here. No, just like even if we did or with 0, I guess that would be, yeah, negative. So yeah, so there are a few ways to go about it. One way would be just so internally JavaScript doesn't really use in integers to store numbers. It stores them as double precision float always, if I'm not mistaken. But then when you do bitwise operations, it actually converts them into integers under the hood. And at that point, it actually figures out that this number is negative because the the leftmost bit is set. So that's why we are getting this strange behavior. This number is neither signed or unsigned. It's a double number, but once we are doing those bitwise operations, it becomes it starts to have a sign. So I think the best workaround would just be to do plus instead of, bitwise operations, and then the test passes and we are happy. And let's do it here as well. We can actually just do plus for the first one, because this one won't have the leftmost bit set, but let's just do this to be on the safe side. So now this test passes, and why does this one fail? It expected this and it received this. So interesting. TSTR1RZ, why does it fail? The result is 50. Oh, let's remove this one so we only see. Why is the result 55? Rn is 1, Rm is 3, and this is 1, this is 3. So what gives? This is 55, and this is 55. All right, so actually we are doing bitwise AND, so it shouldn't be 0 because yeah, their bitwise AND is not 0. We need the numbers with either one of, we can set one of them to 0, and then the result will be 0 and the test passes. So in this case we had a problem with the test, but now we fixed it. We can remove it for filter, all test pass, and we can happily see that we implemented this instruction. And now, before we move on, let's just go back and implement this implement these flags for the LSLS and MOVS. So let's go back to LSLS. Is that this variation? No, that's the one with IMM5, and then result and carry. Oh, so we actually need to take note of the carry, because here we are actually doing a shift and we need to take the carry into account. So we need to do something like that. If IMM, we can do it like that. So const carry is if IMM5, then that's, so we shifted left, so we need to shift left by IMM5 minus 1. Just take the, or we can, so let's see if we had like this. So we had like this, and then let's call those ABC, and then we shifted left by 2. Then B would need to get into the carry, right? Because we removed it, so that would be something like that. That's the carry. So we need to how do they call it? They call it RM. So let's call this input is this value, and then if we didn't shift, then we need to preserve the value of the carry. That's what the datasheet says. Let's create a helper method for that. Get C, return this.ASPR and APSR, not ASPR, and they call it ASPR. I did. It should be APSR. I keep confusing all the time. Okay, so APSR. So yeah, so if IMM5, then we need to calculate the carry. Otherwise, this.get C, the value of C. So we need to implement get C. So and APSR C true, otherwise false. Cool. I'm starting to think it might make more sense just to, instead of doing all those bitwise manipulations, just to yeah, I guess it would just make sense to create Boolean flags for each one of them. That would make the code much simpler. And then if we need at some point to return this as an integer value in the future, we can probably create a method for that. For now, internally, we can just do this. And then this should be Z to be true. And this should be V to equal true. And I think that would make the code a lot more. So let's comment that out. We don't need that at the moment. Much more friendly. And then we don't need all those helper methods. I love deleting code so much. And then here we can just say this.n equals to this. And this.c equals to this. Much more short and sweet, but have we forgotten declaring n? CZV, oh, C what was the order? NZCV. NC, Z, and V. APSR fields. Cool. So this.imn5. So just this.c. Okay. So if this does I and imn5, we need to test that bit that is going to be removed. So let's, if we have 32 bits and we shift by 5, then we need to check. So if we shift by 1, we need to check bit 31, and then if we shift by 2, then 31. So let's do the 0. So 31, 30. So basically, we would need to look at the bit that is input and E32 minus how much we shift, and yeah, let's convert that to Boolean. Yeah, we'll need to add a test case for that, that's sure. Yeah, too many parentheses. Okay, cool. So yeah, so that should calculate a carry, and then we can say this. Can actually don't need this intermediate variable, I guess. And I think here we also need to take into account the carry if we are actually shifting, right? This is Shift C with LSL. What does Shift C do with the carry in? Bit carry in. So if amount is 0, then nothing happens. Shift LSL, LSLC, value amount. So it just ignores the carry. Okay, so we don't need to take care of the carry if we are actually shifting. Yep. So and then that's super easy. If result is 0, this equals result, and then this one if result. And I'm sort of seeing a pattern here, so middle, actually it doesn't really matter, we can just copy paste. Never tell anyone that I said that, but yeah, we can just copy paste, just 2 lines, and then this.c and this.c, and this is unchanged, so we don't need to worry about it. And here with moves, so same logic, I guess, and carry is probably unchanged. Let's just double check that. Okay, we'll check the failing test in a moment. Where is moves? Moves. Is that moves? 0, 1. Yep, that moves. And carry equals carry, but carry is unchanged yet. It just the value of this flag anyway, so we don't need to worry about it right now. And let's see why this TST test is failing now. This should be true, but was false. Why is it false? Because not V, we need to check if N negative, right? It doesn't update V, only updates N. Yep. Okay, cool. So finally we have a another instruction, and we have flags implemented, hopefully correctly. Let's write a quick test case just to see if we did the... I'm not too worried about these two because we already tested them in TST and we just copy pasted them, so it should be fine. But let's just test the carry in LSLS. So basically with carry. So in this case, the carry should be false because we haven't done... Oh, wait a moment. Why do we have a carry? Let's see. That was 80-minute shift. So yeah, there shouldn't be a carry. So perhaps we found a bug. Let's see. So we had we were looking at this bit. So we were looking at bit number. Let's focus on this test for now. Yep. So we were looking at bit number 14, and bit number 14. All right, we need to look at the value of the bit, not ending the input with this actual value. Okay, so now it makes more sense. We are testing the specific bit, which is probably this value. Anyway, so yeah, I'm happy we created the test base because we just found the bug, and then we even didn't need to create a test case. We just added another session to the case that we already have. And then let's create one that does have carry. So if we shift it by 18 bits, that should be 1, 2. Oh, that's long. Let's just do it in hexadecimal. That would be easier. So we want the 18th bit to be 1. No, we want 18. We want 17 zeros. So that's 16, and then 1, and then the rest could be, you know, just like zeros except for this one, right? And then if we take this one and we shift it 18 bits, the result should be this. So we want this to equal this value, which is good. And the last thing we want to do, we want now the carry should be true. Oh, false true is not defined, and it's not true. So what's the problem here? Let's see. So if we take this value and shift it left by 17, 16, yeah, I think we need this bit to be set. Yep. So now that makes sense, and yeah, the test passes. So finally, I don't know why I closed the terminal. We're going to use it in a moment, but finally we have those flags probably working correctly, and we have the TST instruction, and we can move on to the next instruction, which is 394. What is a 394? That's the BNE, branch if not equal n. What does branch is not BNE.N do? BNE, maybe it's under B. Branch condition label, okay, and that's the encoding. So this bit should be okay. Let's, as usual, let's start with the test case. Should Oh, I think N is for like near branch. So basically branch not equal or not 0 probably, if 0 is not set to this address. So yeah, that's the opcode, and it branches back, right? Goes to, yeah. So I think that's -6 because it goes back 6 places. 1, 2, 3, 4, 5, 6. Yeah. But maybe we'll figure out it's -8 like we had with BN last time. I remember we had something with that. Anyway, so the opcode is this one. Yep, that's the right, but the instruction itself is BNE.N. BNE.N. Cool. And then since it goes 6 places back, so we start at 18, and we should be at 12, I guess. Oh, that makes sense. Okay. Oh no, we started 18, but that's 20 actually. Or is it? Oh, it's so confusing. Okay, let's get back to that in a moment. And let's implement this. I think we are still inside B, so that's 1101, 1110. So that's another encoding. That's, yeah, encoding 2, but we want this encoding. That's also the if opcode that's 12. No, yep. We need to extract the. Let's focus on this test. So we need to extract a condition and immediate 8. Let's start with immediate 8. Immediate 8 is opcode and FF. And yeah, it's sign extended actually. So I mean, they add a 0 bit on the right. Ooh, okay. And then if cond is this, then CUDF SVC. No idea what this means. If condition passed. Okay, but what is condition passed? How does that work? Interesting. Let's first of all decode this cond. So this cond is those like the lower nibble of this of the high byte. So in this case, cond is 1. Yeah, so it's 001. So basically, we should do something like if the condition passed, then we should just update PC. But how do we know if it passed? And I guess we need to do this +2 because it worked that way. This instruction. So any idea how we should figure out the value for like condition passed? Let's check if it doesn't get any parameters. Maybe there is no explanation for us. So condition passed. If the current instruction passes its condition check. Okay. Ooh, okay, interesting. So Okay. Okay. Oh, we got it. So we can just basically copy this code, I guess. So yep. Let's just if this check condition cond, then we can implement the logic inside check condition. Let's create check condition cond. Cool. You see, these are like all, this is a cool plugin for Visual Studio Code. It's called Gremlins, I think. Yep, Gremlins tracker, and it shows you if you have some invalid characters in the code. So in this case, those are like not valid quote marks, though they might seem to be. These are like different Unicode characters. But in any case, this is just pseudocode, so switch cond and oh, interesting, 3 to 1. So that's the, actually we need to shift it 1 to the right, and then we can, if it's 0, then result if it's actually false, result equals this.z if it's 1, then result is this.c, and then we have n and v, then so okay, so these are the first 4 conditions, and then we have a few more. So if it's this, then c is 1 and z and not z, so this is z and not this.z. Okay. And then if it's 101, then this.n equals this.v, and if it's 110, then it's this condition together with this.z, right? Oh, and not this.z. Cool. So I think nv, 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 z, z, 110, and then if it's, actually this could be, yeah, result is true, and then if the least significant bit is set, then we can actually return. If it's set, then we negate the results, otherwise we return the result. Cond is 1. Oh, and cond is not 111. Okay, yep. So there we go, and one thing we need to do is to add a lot of break statements, otherwise it will fall through the switch cases. Okay. Okay, oh, and BNE is, I think, branch if 0, and we take the branch if, I guess, we can actually see that this looked at a 0 flag, and if we put a new line here, we'll see that yeah, it took this took this flow, so it negated the result. So it's checking for not 0, which BNE supposedly does. So we need to make sure that 0 is false. Cool. And okay, so branch not 0, and who? Okay, so I think the condition part is working, but let's check it. That was B with cond. Yeah, it took this if, but then this jump went. I think I know what the reason is. If we print IMM, we can see it's pretty big value. First of all, it doesn't look like an 8-bit value. Oh, because we sign extended it, but then I think this should be signed and not unsigned. So I think we did this last time, worrying about signedness. So let's see if there is anything about that in the datasheet first of all. So B cond IMM. Oh yeah, that's sign extend. And I think for this one we also have to worry about the sign then, because it's sign extend as well, like this IMM. Oh, we did this last time, so basically we can probably copy that. Hit a writable variable, mutable, IMM8, and then we just need to adjust the values. That would be 8, and that would be I think 1 and 200 hexa, maybe, or maybe just let's just print the value of. So it gets into this if, right, and then so this is doesn't print it. Okay. I think that should do the trick, right? Yeah, -8. So, okay, so I guess this is correct now. Right, expected 12, received 14. So probably need to adjust our expectations, and magically the test passes. Now, in order to check that, let's add a print here. I am this.pc plus IMM8 plus 2 plus 2. The reason for the other plus 2 is because, first of all, you can see it's equal, but basically at the end of the function I'm going to add 2, and then let's just verify this against the compiled program. So when the compiled program goes to this instruction, we expect it to, so that was the disassembled, we expect the address to be, the target address to be this one. So let's see if this expectation passes. Oh, what happened here? We have a few more instructions that are not implemented. Maybe we jumped to the wrong place. Did we? Why didn't we get this print? Here. Okay, let's run that again and see if we get anything meaningful. Yeah, here. Okay, that's the address we jumped to, and it seems like the legit address, 320. So we are doing some kind of loop here. Okay, cool. But this address, it seems to jump to the wrong place, right? Because then it prints that this instruction is not implemented. This is implemented. Why does it look? It goes here. Maybe we don't. I took the branch. Okay, the branch. So we take the branch twice, and then we get to a weird place. Okay, let's add a few more debug prints. So run link mcu.pc to string 16 branching to. Okay, so yeah, so I didn't save that. So right now I'm going to be printing all the addresses and who. Okay, I now get what's going on here. The reason we are getting this weird behavior is because we probably forgot to add an else. We don't have an else here. So basically what happens, this PC is updated, and then it continues to run through this else if, and it figures out that none of the instruction matches. And some indication for that. While the tests are running, it actually gets to this line, and it shouldn't, because we are only testing instructions that we have, so we shouldn't get this warning. So there is some indication, but we didn't really search on that, so we haven't seen it. So we need this else here, and now you can see that this line is no longer green, like this is no longer executed as part of the let's actually remove the filter. So all the tests are running. It's not actually executed as part of the test suite, so that makes much more sense. And now when we run the code, those invalid instructions should be gone, because it should no longer be executing an instruction after it updated this PC, but before it added the +2 at the end. Cool. So okay, how about now? Is the stream any better now? I tried to switch to a different Wi-Fi network. Hopefully that helped. So please let me know if the stream is any better. I hope so. Thank you, Casey Martinez, for letting me know. Cool. Anyways, so we are stuck inside some kind of a loop here. You're welcome. And let's see. So we have this loop, and we say that this is the loop. It reads from, that was 390. Okay, cool. So this is the loop, and this loop reads from this address. The value stored at this address +24. So this is this value, which is the UART. So let's see what's in this UART at 24. So 24 is 18 hexa, right? Let's double check. Yep. So it's looking at the UART flag register, UARTFR, and I think, yeah, we can see those reads. Not here. Yeah, we can see those reads from the UARTFR. And let's read about the UARTFR. So the UARTFR have a few flags. And which flag is it looking at? It's looking at this is the part where it's reading. Yep. So it's testing it against R1, and R1 has this value 32. So basically 32 would correspond to 20 hexa, or it's like bit number 6, right? 0, 1, 2, 3. No, bit number 5. So it's looking if transmit FIFO is full, the meaning of the bit, and then it reset. This is set to 0. The meaning of this bit of FEN, if the FIFO is disabled, this bit is full when the transmit FIFO is full. Okay, so it's looking at this register too, and basically it's branch not equal, branch not 0. So it's looking at this bit, and apparently, so it's reading this bit from this address, from this memory address, and apparently what happens, we don't have anything at this memory address. So what do we do when we don't have anything? We return all ones. So it says all ones, and then it thinks that the transmit FIFO is full, so it keeps looping. So it's a like busy wait for the for this bit to be 0, for the FIFO to be empty. So I think we now need the reads from SAO space. For that, we're going to start implement some kind of mechanism that will allow external code to hook into addresses and implement, read and write, like implement hardware registers. Eventually, this code will be part of a different class that will have one class for each peripheral. But for now, we'll just put it inside the run Blink code just to, it actually should be now run UART TS. So let's have read hooks. And read hooks is basically a mapping between numbers, which are memory addresses, and callbacks. And those callbacks, read callback. And actually, we need to create a new map. Yep. And those callbacks are basically just basic functions. So let's define this interface, export type. Actually, it doesn't need CPU, just CPU. So they take a memory address and they return a value, a number. And then what we need to do here, we need to say if we can put it in else for now. Maybe in the future we'll want to have hooks for like addresses inside the RAM or the flash, but for now we can just if it has this address, then just return this dot read hooks dot get at this address. So const hook equal, and then we can return hook with this address. And it's not happy because hook is possibly undefined. So let's do it like that. Const hook, and then we can do if hook, then return the hook, otherwise just return this default. No, if hook, then return this, otherwise just print the warning and return this default value. And maybe the default value should be zeros and not Fs, but let's worry about that later. This actually let us figure out that there was something wrong because we got a value we didn't expect. So at that point, we can start implementing the hooks and we can say something like mcu.readHooks, and if anybody is reading this UART register, which is at we got the address here, simply return 0. So this will always read 0 for now. Oh, that's a map, so we should code set and a function that returns 0. Cool. So this is the syntax for an empty function that returns 0. It always returns 0. And now if we run the code, yeah, we can see that now it got past that loop because it's reading from a different address, but now it's stuck in a different loop from some address that seems very random. But first of all, let's reduce the number of instructions so we can see what's going on here. Run it again. And yeah, and we can already see like that BL is ignored, we know that. And then we get, so this is the loop, if I'm not mistaken. And then we probably get past the loop and we have 2 instructions that are not implemented. And then we are reading from this memory address. So it could be that the memory address is wrong because we are missing these 2 instructions. Let's check what they are. So LDRSH and CMP. So what does LDRSH do? Let's create a unit test and then figure out. I guess it loads something from the memory. LLL. Yeah, let's move LDR before MOVS. So to keep those sorted. And this one should also go before move. Just keeping the test sorted alphabetically. Okay. And let's see what we got here. We got LDRSH. So LDRR3, LDRSH, R5 with this happiness. So LDRSH R5. And the opcode is this. And now we need to read about what it does. So we can write the test case. But we already know we will need some value inside R3 and R5. So the second operand is always where we are reading from. And we will need to assert on R5 because we are probably writing the result to R5. So we have the skeleton of the test and we just need to figure out the actual content of the test. So LDRSH, where are you? LDRSH, yep. Load register signed half word. Value and offset loads a half word. Half word is just 2 bytes. Sign extends it to form 32-bit word and writes it to register. Okay, so we do a few things here. We have RM, RN, and RT, 3 registers. And then we basically calculate the address. So what's offset? Offset is RM. So basically, add is probably always true. Yeah, and index is always true. It's pretty repetitive. So we take RM, shift it by 0, like before. So we don't do anything with it. And then add is true. So we add this to RM. And then address if index and the index is true is this. So we read a word. No, so we don't read 32-bit integer, just 2-bit, 16-bit integer. This is false, and then we sign extend the result. Cool. So for that, we would need to do this kind of setup. So we can just set R3 to be this value, the beginning of RAM, and R5 to be like 6 bytes into the RAM, and then we can put there some value, and we only need to put a 16-bit value, and in order to make that interesting, let's put a negative value. So this value should be sign extended. So 7 and 6. And then we expect the result in R5 to equal the same, but sign extended. So it should be this. And we got a test case. Now to the instruction, which shouldn't take too long because we have LDR already, and it's pretty much the same, I guess. Just we just need to take care of this sign extend. So LDR. That's one of the things that makes it fun to implement CPU architectures. Once you get like the base setup, and we pretty much got it here, it goes really fast. Like you can start churning instructions at a pretty high pace. So what do we need here? We need RM, RN, and RT. Each of them is like 3-bit. T, N, and M. So cool. And just like these bits. And then we just need to add them, right? RM and RN, right? Or RN and RT. This is confusing. No, RT is the result. So we are adding RM. Yeah, it makes sense. T is probably target. And then we need to just read uint16 instead of 32 from this address. And we also need to sign extend it. How would we do that? So let's make an helper function. Function sign extend 16 value number. So basically, if value, if this bit is set, then actually this should just be 8 and 8. We don't want to set all the other bits. Or you know what? We can leave it F. Just the result would be this. No, it would be this. So the most significant bit moves to the left. So if this bit is set, then we return this bit set. We move this bit to the left, and value. Okay, we don't want to go negative. Yeah. Otherwise we just return, so return this, if this, then do this bit wizardry, otherwise just return the value as is. Okay, so why doesn't it pass? Oh, we still need to implement read uint16. So what we can do for read uint16, we can just, read uint32 and return the no, that would not be good. Endless recursion, and return the return the 16 lower bits. Cool. So so received 6, so probably we don't write back the result correctly. Let's see. That was this instruction. Oh, right. Something is wrong because we don't use RN. It's unused. Okay, cool. Let's focus on this test. Huh? Interesting. Oh, I know. This actually doesn't run anything because we forgot to, you see this code is not executed. We need to do this as well to check this bits. So these are like 9. Okay, so now the test passes and we are happy. This works, yes. Another instruction. So I think if we restart it, we should see that that instruction is now implemented. It's no longer complaining. It's still reading from this weird memory address though. And we still have one more instruction we need to care of. And I think it was this CMP instruction. And I think CMP is just super simple. It will take us a few moments to implement. So BN CMP. Usually, if it's like x86, then it just calculates the difference between the two numbers and or the value of R5 and 66 and update the flags accordingly. So this is the instruction. And we know it will need R6. Let's make it 60, R5. And this is the opcode. Cool. And then, let's check the datasheet. But I'm pretty sure this is going to just look at these numbers and update the flags. Let's check it out. Where are you, dear datasheet? CMP, CMP, CMP. Cool. So that's CMP with immediate. So CMP does 0 extend, and then we need to take care of this 0 extend. I think we already have 0 extend, and then it just add with carry and updates result, carry, and overflow. Oh, finally we are doing something with overflow. So this is the opcode. Let's start with the opcode. Let's start with the test. So if we are comparing these two numbers, then let's see. Oh, so it's actually adding with carry. Oh, it's doing not. Got it. So probably a fancy way to subtract two numbers. What is that? That's not overflow? Huh. Okay, so in this case, I guess we expect 0 to be false, because the result won't be 0, I guess. False, and then we expect CPU.carry. Not sure, we'll figure it out in a moment. And we also need to check CPU.N and CPU.V. Okay, we need to understand what it does in order to figure out our assertions. Okay, LDR, CMP. So else if opcode blah 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 opcode is this, then we can we need to implement 0 extend. We need to find out IMM8 and CMP. Where are you, CMP? Okay. Const IMM8 is just opcode and FF, and then RN is opcode shifted by 8 and 7, right? That's 3 bits. Yep. And then we will need to 0 extend 8. We already have 0 extend That was zero sign extend, we call it. So that's zero extend. Oh, so it's easier. We don't need to worry about it. So basically, if it's not sign extended, then just adding zeros, we don't care. And then we need to do this. So add with carry. What does add with carry do? So first of all, we need to let's call it result. So that's this dot registers rn not IMM8. Okay, and then there is this one. So let's see what add with carry does. Add with carry, it gets two numbers and carry in. So in this case, we said that carry in is 1, right? So basically +1, I guess. And then there is carry out result. So there is unsigned sum and signed sum, and result is unsigned sum. So overflow is if signed sum. Okay, so uint result. Okay, so basically overflow means if the result is over the limit. But what's the difference between overflow and carry out? If uint result, let's copy it and try to figure it out. So if uint result, so if we had like something like this, for result, then sint result then sint result would be, what's the difference between sint result and -1? I'm actually not sure. Maybe there is a better explanation about overflow, what it means. The result. So n -1 to 0. So let's see this section. Addition and subtraction. Okay. So basically, we are taking. So if the result is n bits, I guess this would always be true, but okay, let's just try to look at some examples. So if the signed sum is this and the unsigned sum, oh, got it. So yeah, so the unsigned sum could be something. So if we had like this number, and then we add -1, which is, so this is signed -1, and we add another -1 to it. So I guess unsigned sum would be something like this. Basically overflowing, and signed sum would be -2. And then I guess in this case result would just be taking this bit, so that would be result. And in this case result is actually equals signed sum, so that's not an overflow, but uint result is not equal to signed sum, so we had a carry. Interesting. Okay. So we had the result doesn't equal unsigned sum, so carry. And let's see if we can get it the other way around. So okay, so if we have something like, so result is like very, okay, so yeah, we have different example. So if the first number is like this, which is minus max int, like minus 2 billion something, and we add to it, well, that would overflow anyway. Oh, so if we add, I'm trying to think if there is a way we can get that would, oh, wait a moment. So that would not get us carry, but that's max int. So I think that would also not get us overflow, right? We would get, the result would be just so that's -1, which is that's actually max int means -1. So in that case, result would be, we would not get carry nor overflow. So I'm trying to think if there is a case where we would get overflow but not carry. So the sum of the oh, we also got this carry in, which is, no, does it matter? Hey David, thank you for joining. Yeah, I'm trying to figure out how the overflow is calculated when adding two numbers, or in other words, if there is a case where we have overflow but not carry. Anyway, we should just like take the lower 32 bits of this, and then I think the first thing we want to do is to store this result somewhere. So this.registers rn equals result. Okay, so in this case, let's see, we are adding this and not this, so basically that's +1 because we have carry. So basically 60 plus not 66, right? That's this, not y. Okay. Oh, right. There is result with overflow. Okay, this might help us, because in this case carry in is this is like x not y and carry in. So result if carry in is y, which is result is x minus 1 with overflow 1 if signed overflow occurred during the subtraction, and carry out 1 if signed borrow did not occur during the subtraction. That is if x equals or greater to y. Yes, Tony, I think that's what it means, but they actually give us nice shortcut here. So if carry n is 1, then result is x minus y with overflow 1 if signed. So in this case, this is the case because we are doing add with carry x not y and carry in. So we are basically did I delete it? Why did I? Or didn't I? Yep. So we are basically doing so result is basically rn minus IMM8 minus IMM8. So these dot registers rn, or that's we don't store the result here. We don't care about the result because this is CMP. We just ignore it and just update the flags. So basically we can say this. So first of all, the result is 0 only if they are equal, right? This dot registers rn, and then we have carry in is 1. The result is that with overflow if signed overflow occurred during subtraction. Okay, and carry out if unsigned borrow did not occur during the subtraction. That is if x is greater or equal than 1. So let's see if is greater or equal. Cool. And then overflow if we didn't have signed overflow during the subtraction. X minus 1 if signed overflow occurred during the subtraction. What does it mean if signed overflow occurred during the subtraction? So signed overflow is like what we had here, I guess. -1, -1, -2. Yeah, so yes, we can say that overflow. So we can say yeah. So first of all, that's the v flag, and we also have the n flag. What happens with the n flag? In this, we were inside CMP. So n flag is just the whether the result is negative, right? So let's say this does n if basically rn is smaller than IMM32, right? Then the this.registers. Maybe we'll store this into another variable instead of like repeating it 3 times. Okay, so value, and then what's the IMM8? So basically that's result carry overflow. I don't need all that comments, and then I'm just missing v. So v is true if we had a signed overflow. And how do we determine that? So we had a signed overflow if let's try to Google that. What do they mean by signed overflow? If their signs are different, then overflow 4. If the same, A minus B. Okay. So basically, if their signs are different, so if value is greater than 0 and IMM8 is, oh, we need to convert them to signed. To sign extend them for that. Okay. So first of all, we don't really, oh, we do need a result. No, we don't need it. Yeah, but we assume that it's there signed here. Yep. Okay, so first of all, we'll make sure this is by doing OR0, we are actually telling JavaScript. So if it's like this number and we are ORing it with 0, we force it to convert it to 32 signed integer. And yeah, and then we need to convert this one into signed integer as well. So let's sign extend 8. Let's implement sign extend 8. So sign extend 8 will just take the value and just like sign extend 16. Very similar. All right. Cool. So this that was CMP. Okay. And then this is so if they are equal, actually I'm not sure if we should sign extend them before we, yeah, we are checking the result, so I think we should sign extend them when we are adding them. That's here. That was CMP. Yeah, we are looking at the result, so I think we should sign extend them. And then if this is da 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 da, and then so if their sign is different and the result is the same as the same sign as the subtrahend, and so in this case we want the result to be less than 0, so we want so if value is greater than 0 and we need to let's just calculate the result. Value minus IMM8 and make it 32-bit unsigned, and then we can probably check this condition or this. Cool. So value is greater, and this is greater, and the result is greater. Yeah, sort of makes sense now. Okay, so in this case, we are doing 55 minus 66 minus 60. So the result is not 0. The result is not negative. And I think there is no carry. There should all be false, right? That's CPU RP2040. Oh, and the result should be just 6. No, there shouldn't be. We don't change R5. Okay, and why we get true here? Let's print the result. -6. Okay, we are doing. Oh, it's negative. Yeah, we are doing 60 minus 66, so it should be negative. It shouldn't be 0. There isn't carry, which makes sense, and there isn't an overflow. Okay, cool. So we sort of have CMP implemented. I'm not sure if the implementation is 100% correct, but let's leave it for the next time. Let's just, hey Anderson, if by the way anyone wants to contribute a few more tests for this code during the week, then feel free. I'm really happy to get pull requests. Now that we have CMP, or sort of CMP, we can see that we are, oh, we still missed this instruction. What's this instruction? We still have one instruction missing here. No, wait a second. We already have CMP. Why does it claim it doesn't recognize this CMP? Oh, that's CMP between two registers. So let's quickly implement that. That should not take as much as the original CMP, because we already have the logic figured out, or so we think. So this is the opcode, and R5, R0, and then let's do, so that would be R5 and R0, so R5 minus R0, so let's put 56 in R0, and then let's focus on this test, so it only runs this one, and we can probably implement this other CMP, CMP register. So this is the code, else if, so that was CMP, right? Mediate, and then we have CMP register, else if code, I think that's 6, yeah, 6. So if we have this opcode, then we need to decode RN and RM. Oh, there are two versions. Oh, what's the difference? Okay, so let's just mute my phone. Okay. Yeah, this is the version we have here. So RN is this lower 3 bits, and RM is the next 3 bits. And then 0 shift as usual. And then I guess we just do the same, right? Shifted is RN minus RM, and I guess it's the same logic. So we have, let's call them left value and right value. Right value and left value is RN, right is RM, and then we basically do the same but with these registers. So now if we had the logic wrong, now it's wrong in 2 places. Amazing, isn't it? And then we expect it to be false, and oh, we had a carry here. Why did we have a carry? 60 minus 56. Oh well, I'm too tired right now to debug it, so let's hope this is true. But yeah, if you figure out it's not, let me know. And probably I will check it out during the week. And yeah, now we have all these instructions implemented, and we have these weird reads. Where are they coming from? These instructions, 3C6. What's it? 3C6 LDRSH R2 plus 24. R2 is loaded from this address. So it should have this value, but for some strange reason, it holds a different value. So probably we did something wrong somewhere along the way. Anyway, I'm starting to get pretty tired, so I'm not as focused as before. So I think we will wrap up. We added a few more instructions, but I think we also laid the ground for the future by adding all these sign extended and these flags that we were missing, and we also added these read hooks, which is going to be super useful once we actually started implementing all the peripherals. Yeah, I mean, we have a few more tests, and I think it's a good time to call it a day. So let's commit. Let's just remove all these. I don't like those commented out. Thank you, Casey. Let's remove all these unused. I don't like those commented out stuff. Cool. Yep. Cool. So let's commit this, and we can also commit this, I guess. And then let's just remove the test filter and see that everything passes. Where is the test filter? Goodbye filter. Yep. Yeah, and then we can see like all the tests that we added. We sort of doubled the amount of tests. We moved some tests around, so but yeah, we added a bunch of new tests and all the new instructions. Yeah, we added pretty much a big interesting chunk of code. So fit implement more juicy instructions. Yay. To do check if we got the carry/overflow logic right. So I will try to check it throughout the week to figure out if we got it right or not. So unfortunately, after this commit, our code will no longer blink because we no longer load a blink example. Now we are trying to write to UART, but we are not there yet. But I'm pretty optimistic that there is like some loop here that reads from a random address, which is strange. But I'm pretty optimistic that once we figure out that bit, we don't have a lot more left to get the UART working. And I might be wrong, but I think we have all these instructions covered already. So we should have it working within a few minutes, probably. Like we have all those branches already, and all those conditional branches should be covered by what we implemented. And I'm not seeing, okay, there are a few more instructions like addS, subS, neges, so yeah, so there is still a load byte probably. So there's still some work, but I think we'll get there in the next session. And let's commit this. Just a moment. Yep, let's do those ones. Why is it unhappy? Oh, we are importing those and they no longer exist. My bad. Okay, cool. Coded during the second live coding session. Okay, and before just the instructions. And before we sign off, just one more question, and you can answer it in the LDM and STM. You can answer it in the chat, or you can write to me later if you like. We have the Discord channel. I will put the link now in the chat so you can have it. That's workway.com/discord. Would you like us to continue from exactly the same point next week, or I can just, implement a few more instructions myself? So I don't know if it's interesting for you to watch me as I go and implement the instructions, because it's starting to get a bit repetitive, I think. But it might still be interesting because we are seeing all these like edge cases and things that I didn't anticipate. So I would love to get your feedback on that. If you want to continue from exactly the same point, or if you want me to implement some more instructions, or maybe just, get the test cases ready before the next session and just implement the instructions themselves. Okay, good feedback from Jason. All right, so cool. And one more thing, I guess some of you already know about it, but there is a link where you can okay, I got the feedback. That's great. There is another link I'm going to share here. That is, I think let's just let's first push and double check this link. So no, 2040. You see, I'm tired. Yeah. So I opened this simple page where you can sign up, and I will just send you a reminder before each session, so you don't have like to remember or like go to the YouTube channel and look for the stream. We will just get the link to the stream in your email just before we start. So if you want, just go to this page. I shared the link in the chat, and yeah, and just sign up and get the updates for the next week. Okay, so I guess that's all for today. We have done some more work. We almost got the UART working, or so I want to believe. And see you next week. Bye bye.